Hey everyone, welcome back to the Chain Reaction Podcast. I'm your host, Tom Shaughnessy, a co-founder at Delphi Digital, where we're 5 full-time analysts focused on institutional crypto research. If you aren't a subscriber, you're missing out, so visit the site while you're listening. One quick housekeeping item. This podcast is strictly informational and educational and is not investment advice or solicitation to buy or sell any tokens or securities or to make any financial decisions. I may personally own tokens that are mentioned on the podcast, and you can view the show notes for our full disclosures. Hey everyone, welcome back to the Chain Reaction Podcast. Today we have Dan from Vision Hill Group, who's back for episode 2 of our educational series. As a reminder, our last episode with Dan was on distributed consensus. For those that may not have listened to our first episode, this is a multi-part series focused on simplifying complex subjects for many in the crypto community. This focus will be on scalability, a hot topic that has more often been at the center of debates in the industry for several years now. If you're listening to this podcast and have a particularly complex topic for us to cover, I encourage you to reach out with us with that topic so we can look into it for future episodes. Lastly, I must disclose again that all topics discussed in this episode are strictly informational and should not be taken as investment advice now or in the future. So turning to Dan. Dan, welcome back to the podcast.
Thanks, Tom. Excited to be here.
So today you and I are going to focus on scalability for the listeners. It's quite a heavy subject, so I think it might be helpful to break it down into a few topic areas. Perhaps we can begin by discussing what scalability actually means and why it's so important, and then we can get into where we are in terms of scalability as we're nearing the end of 2019. Maybe we'll go into some examples of certain projects and then end the conversation by discussing scalability on layer 1 versus layer 2.
Sure, that works well.
Awesome. So Dan, what exactly is scalability and why is it so important?
So I think most people have developed this notion that scalability refers to performance, like the speed of which a network can operate measured by a metric, something like transactions per second, which is abbreviated as TPS. So when you look at a network, especially a payment network like Visa that claims it can handle up to something like, 24,000 transactions per second or something like that at maximum capacity, and to compare that to networks like Bitcoin or Ethereum that handle far, far less. I think Bitcoin currently averages roughly 3 to 5 transactions per second. Ethereum handles roughly, call it 15 transactions per second or so. I think with that comparison, it's pretty easy to create this general view that blockchains are simply not scalable at this point in time. And while that is one way, or rather one approach to defining what scalability means, I don't think that's really the full story. So I think there's a lot more going on under the hood than simply looking at a metric like transactions per second or thinking of it in terms of performance, which is sort of, I think, what most people do. And I personally believe you have to consider a lot more. You have to consider things like costs, which are the transaction fees that secure a network. You should consider the number of validators that are incentivized to participate and secure a given network. And ultimately, I think you have to think about the user base, which is sometimes referred to as social scalability. All of those parameterizations, the cost, the number of validators, number of users, all of those have to scale in a sustainable manner collectively. So it's not just about how quickly transactions can be processed. It's also about the social scalability that I was just talking about. And one last thing I'll say here is we also need to consider finality. This is a topic that you and I discussed in the last episode, Tom, but I think it's so important because the type of finality inherent in a protocol is absolutely vital for the security of any given single transaction.
Yeah, I couldn't agree more, Dan. The finality aspect is something a lot of people miss, especially new layer 1 chains where they focus on cheap transactions and high speed, but they don't really take into account the finality guarantees that are inherent in Bitcoin, which are immense. So if we dive a little deeper here, could you explain why there's such a large gap in performance between networks like Visa that claim, tens of thousands of transactions per second, and then blockchain networks that are significantly lower by comparison?
At the moment in a blockchain network like Ethereum, for example, every single transaction has to be processed by all the nodes in that network. This is part of the consensus process that we talked about in our last episode. And there are many obvious challenges with this. So for instance, in 2017, there was a single Ethereum application, as many know, CryptoKitties, that became so popular that it clogged the network, slowing basically all transaction processing nearly to a halt. And a couple of problems emerged from this, such as high waiting times and high fees, because anybody wanting to start a new transaction was essentially placed in this long queue of transactions that were all competing to inherently get placed into the next block on the chain. So on top of this congestion and competition for having each transaction get processed, which is driving up fees and waiting times. I think what most people may not realize is at its peak, CryptoKitties only had something like 14,000 users, which is really not that big when you compare it to a traditional network like Visa or MasterCard. So the culprit, I think, is every node historically has had to process every single transaction. And this poses challenges when you want to scale to millions or even billions of users. And therefore, I think many in the industry, including myself, have developed this notion that networks need to sort of evolve away from the idea that every computer, every validator is required to verify each and every transaction, and instead transition to a model whereby a validator on average perhaps verifies only a small portion of the transactions on a given blockchain instead of every single one. So this kind of proposal for improved scalability would be expected to bring costs down by a meaningful factor, since it's able to boost the processing speed, which we can refer to as throughput. So I guess to wrap that up, the goal is ultimately to make the verification process for small contract platforms and transactions much more direct and much more streamlined by verifying only a smaller portion instead of every single transaction.
So, what's the state of scalability today? Like, we're almost approaching the end of 2019. Are we close to cracking scalability? I mean, for somebody that hasn't been paying too close attention to developments over the last year or so, because I don't know if all of our listeners, spend a ton of time on this. What can you tell us?
I would say we are certainly getting much closer to cracking scalability. The amount of progress made in the space over the last, call it 12 to 18 months, both in research and in actual development, has been truly quite remarkable. So we've learned a lot as a community, and I think we're really starting to get very, very close, particularly at the layer one level, with layer two expected to follow shortly thereafter.
Yeah, for sure. I mean, I know there's dozens of teams working on layer two scaling on Ethereum, and some of the names will probably, most people will know, like Connext and Scale, and even Loom Network. And then there's 7 different implementations of the Lightning Network on Bitcoin, and I think that's doing pretty well. So switching gears, so sharding seems to be a popular approach to cracking scalability at layer one, the base layer. And we've seen with Ethereum 2.0 in its roadmap, and it's also in projects like Near and Definity. Can you help us break down sharding and discuss other approaches taken here as well?
Sure. So sharding is indeed a popular approach. And essentially, sharding refers to partitioning a relevant blockchain network into a multitude of parts. And these parts are simply referred to as shards. So it's basically the easiest way to think of it is a divide and conquer approach, very generally. And a little more specifically, sharding allows for some specific node to be coupled with some specific shard, meaning that all nodes do not need to run through a blockchain network's whole entire transaction history for verification. So this is what I was referring to earlier. Like, instead of verifying every single transaction, you just simply verify a small subset of transactions. And this substantially increases the number of different transactions that are able to be processed by a blockchain network. Several different nodes on the network can, cooperate, can coordinate, and divvy up transaction processing amongst, this designated group of network computers. And as a result, more transactions can be processed at the same time. So in sum, I think sharding enables a network to evolve beyond the need to have every computer verify every transaction, because instead connected validators are essentially verifying a small portion of the transaction on average. And this inherently boosts the throughput and can lower the cost as well, since, as I was talking about earlier with the problem that CryptoKitties showed us is that transactions aren't all competing to be placed into a block at the same time.
That's a really helpful breakdown, Dan. So, looking ahead, like, why do you think sharding appears to be so complex to understand today for people that aren't particularly technical?
Well, in essence, sharding is a extremely difficult engineering problem that has rarely been successfully implemented in the space. So even where we are today, sort of nearing the end of 2019, I think research roadmaps across many of these projects are still very fluid, and ultimately specifications are not yet finalized. And as a result, it could be very hard to grasp sort of the current state of affairs at any given time, since things are constantly iterating, constantly changing. And not to mention the technical areas are very complex here as well. Without going too deep here, if we recall from our last episode where we discussed distributed consensus, you know, distributed systems sort of lack a global clock, but they still need a way to determine the order or the sequence of events. So for instance, I paid you and you paid me and so on. Who paid who first, and how do we check the balances to make sure that there was enough in the balance to enable the payment transaction to go through? So in the case of sharded networks like Ethereum's 2.0 roadmap, each shard only communicates with the beacon chain, which is essentially the main chain, on a periodic basis. And this can create a challenge of something called inter-shard latency. Latency here simply refers to the length of time it takes to transmit data. So the lower the latency, the lower the length of time it takes to transmit data, and the better it is because it's higher speed for network processing. So going back to the question of why sharding is seen to be so complex, if we think about the global state of a sharded system being locked until there is communication between shards to determine the order or the sequence of events, such as checking the balances, as I used as an example before, in order to enable transactions to go through. Even sharding can potentially run into some scalability limitations at a certain point, and we'll get into that. So this goes back to why it's still so much of a complicated engineering problem. And I think this is where the Ethereum community is currently. In the cases of Neo and Definity, things are a little bit different. Neo no longer uses a beacon chain, and Definity has something called threshold relay. But the point remains the same, that sharding certainly can be a solution to layer one scaling, but it is quite challenging to engineer, particularly in the case of cross-shard communication.
Yeah, I couldn't agree more, Dan. I mean, I remember looking into this, months ago, and there was 5 or 6 different potential approaches to handle cross-shard communications on Ethereum. And then, you have the new layer ones you mentioned, like Near Infinity, that can basically build from scratch their way, because they don't have to re-architect an existing network. They can start from scratch. But moving forward, what are some other examples that you can speak to concerning layer one scalability?
So there's quite a few. I think perhaps the most interesting to discuss next is the separation of time and state. Other examples include interoperability, such as achieving scalability through parallelization of computing, and perhaps we can get into that in a future episode. Some other approaches that leverage zero knowledge proofs, (ZKPs), are also potential solutions to scalability. Zero knowledge proofs are some kind of cryptographic magic, and we can cover that as well if we have time today. Otherwise, perhaps we can do that in future episodes.
Yeah, I mean, interoperability is a fascinating subject, and it definitely deserves its own episode. So we'll definitely do that in the future. But let's go deeper into the separation of time and state. What can you uncover there?
So if we recall from our sharding discussion just a few moments ago, we addressed how distributed systems and blockchain networks are essentially locked until the sequence of events can be determined. So although there is no global clock in these networks per se, there's still a notion of time such that the order or the sequence of events can in fact be determined. So time is here without a clock, if that makes sense. And this is covered in depth in the distributed consensus research that we published, if any listeners are interested in going deeper here. But in essence, the best way to think of this is, in order to increase throughput, which is the speed of processing transactions, historically, a protocol would either need to increase the block size, and the Bitcoin Cash fork is an example of this, or the other option is decrease the block time, which is essentially sharding. But we'll get to that in a second. The point is, time and state have essentially been coupled since the birth of Bitcoin. And with sharding, like I said earlier, you essentially have this divide and conquer approach that allows the global state to be broken into a bunch of smaller pieces. Each of those pieces has its own independent process in time, and each of those pieces also has the ability to progress independent of the others. So while this does increase throughput, it's important to recall what we discussed earlier. In the case of Ethereum, each shard will only communicate with the beacon chain periodically. So current research shows that this is done in something called slots, and slots are each expected to be approximately 6 seconds in duration. And this can create our potential challenge of inter-shard latency, because if I want to send a transaction to you, for example, and I'm in shard A and you're in shard B, and assuming that you give me your wallet address, what we're dealing with here is essentially the validators have to prove that they burned my tokens in shard A before the validators in shard B will mint an equivalent amount of tokens to you. And therefore, the global state of our blockchain network is locked. It won't allow any further transactions until there is communication between our two shards here to determine the order or the sequence of our events. So I can't pay you until I've actually burned my tokens on my shard, which is shard A in this example, and you won't receive the tokens in shard B until my tokens in shard A have been burned. So that communication, the 6-second times, that can create some scalability limitations as things currently stand.
Excellent. I guess that's a great overview, Dan. And I guess so it seems that the increase in throughput from sharding could lead to a delay in finality between the shards, which could be somewhat counterintuitive, but it makes sense when you walk through it. So let's go back to the separation of time and state as another approach to cracking scalability.
So in this exercise that we just went through, we see this challenge of how to accomplish faster time and state updates starting to manifest itself. And essentially, one approach to solving this is to separate them. So Solana is a project that's doing just this. They introduced a global clock that is expected to be a trust minimized clock that can progress the notion of time without necessarily updating the global state of the chain.
So without getting too technical, Dan, could you explain how exactly Solana does this?
So if you think about a network like Bitcoin, where each block contains the hash function of the previous block as one of the 4 components in the current block, this is essentially how blocks are quote unquote chained together. So in the case of a network like Solana, rather than chaining hashes together every single block, where every single block includes a multitude of transactions, instead, Solana is chaining the hashes together into a block instead. And what this does is it essentially encodes the passage of time in a data structure that is referred to as proof of history. And through this mechanism, Solana claims that they can scale up to 50,000 transactions per second. And now whether or not that is true remains to be seen, but it's certainly an innovative approach to scaling.
Yeah, I agree. It's definitely innovative. It's an interesting structure, and it'll be interesting to see how it all plays out. I think it's important to emphasize that we touched briefly in the beginning of the episode on the notion that scalability is not just technological, but it's economic and social as well. So history's taught us that the best product or technology doesn't always win. Most people think of the VHS example and Betamax. So I'm really curious to see how this all pans out, because while some of the tech approaches you discussed earlier may be able to compete with networks like Visa on TPS, they may not necessarily become the winning blockchain networks if they don't capture the economic and social scalability as well.
100%. I fully agree with you there.
So just looking at the clock here, we're starting to run a little light on time. So one last thing I wanted to discuss with you is the notion of scalability on layer 2 compared to layer 1. Everything we discussed so far represents layer 1's approach to scaling, and you had an awesome discussion there. Can you briefly break down what's happening on layer 2?
Of course. So for starters, I think listeners should be aware that you, Tom, actually covered this topic pretty extensively in one of your fantastic Delphi digital reports. So I'd encourage listeners to contact you regarding getting access to that. The primary difference between layer 1 scaling and layer 2 scaling, as I understand it, is layer 2 approaches essentially rely on layer 1 for security. So these layer 2 solutions somewhat sacrifice security by requiring a little more trust, and that trade-off is made to garner greater scalability. So some very good examples here are the use of state and payment channels. These are projects like the Lightning Network that you mentioned earlier that's building on top of Bitcoin. And some networks building on top of Ethereum include Plasma, Connect state channels and counterfactual state channels, the Spank chain and Funfair payment channels, and so on. So these layer 2 approaches essentially say what we're going to try to optimistically do is we're going to set up a separate consensus layer where people perhaps do trust each other, or at the very least cooperate with each other. And if for whatever reason that can't work, such as if people can't reach agreement, or if perhaps somebody is being malicious, those people can always revert back to the main chain, which is layer 1. So in essence, layer 2 assumes layer 1 is the extremely secure, trust minimized consensus layer that is very slow but very secure, and fundamentally distinctively assumes people can trust each other and agree with each other a little more flexibly at layer 2, and thus earn performance efficiencies as a result, because if for whatever reason they can't, they can always go back to layer 1. So layer 2 essentially relies on layer 1, but could potentially be used much more than layer 1 depending on the application.
That's an excellent overview, Dan, and thanks so much for the kind words on the report. It's a really helpful way to frame it. So what are some examples you can give on these layer 2 approaches that may integrate themselves into our everyday lives?
So let's say that you and I are both very big gamers and we want to play something like decentralized tic-tac-toe. Very simple example here. What we can do is we can commit with skin in the game that we would like to engage in a game of decentralized tic-tac-toe, but rather than making and verifying each and every single move on the layer 1 chain in a highly secure but slow fashion, what we can do is we can play much more expeditiously off-chain by individually agreeing on each move. We are essentially trusting each other with the so-called off-chain state update. And then finally, at the end of our game, we can collectively agree on the final state that determines who the winner of our game is. So during our game, we can trust each other because we each sign each transaction instantly, and the game concludes with the final state update that goes onto the main layer 1 chain. This is essentially how state channels work. And on the other hand, a solution like Plasma is conceptually very similar, with the key difference being every transaction that happens off-chain actually does not have to get signed by all the participants in the channel, rather than being instantly verified. Instead, what there is there's some kind of designated operator that aggregates and verifies everything periodically, but it's still done off-chain.
So to summarize, would you agree that for the end user, state channels are good for circumstances where you want instant but fee-based updates for a fixed group of people, like tic-tac-toe, poker, and chess? And then plasma channels are good for when you want to have free updates for publicly autonomous information, like a marketplace or an order book or things like that?
Exactly.
Awesome. Well, Dan, thanks so much for coming on. I'm really looking forward to continuing the simplification series with you on future projects. It's become one of my favorite series that we're doing because it's just simple, to the point, and you just share a ton of great information in a short amount of time. So if anybody has any questions regarding what we discussed today, you can always reach out to Dan or myself on Twitter. And Dan's Twitter will be linked in the show notes, as well as Vision Hill Group's site. Dan, thanks so much for coming on.
Thanks for having me, Tom.
Hey everyone, thanks for listening to the episode. If you can go to iTunes and hit subscribe to the Chain Reaction Podcast, it'll go a long way in helping us reach new listeners and help support the show. Thanks again.